Hi, I'm so excited to share with you today a culmination of work that we've been doing with Xilinx over the last 2 years, having to do with machine learning at the edge for industrial applications. My name is Richard Elberger. I'm a partner solutions architect in the IoT segment in the AWS Partner Network. What we're going to go through today is first some tenets, some guardrails to help you understand the main paradigms that fit into when you're doing industrial applications at the edge. Then we're going to go through the industrial IoT architecture, which is a curated architecture that we share with our customers. And we'll be able to understand how the story that we're going through fits within that architecture. Then what we're going to do is break down how this machine learning at the edge fits into a 4-part iterative lifecycle story. Let's go ahead and get started. The first tenet that I want to share with you today is about effectively maintaining the system over the life cycle. What we want to be able to do is manage and maintain these systems over their lifespan in a hands-off, iterative way. We want to be able to update these systems across ecosystems without human intervention at each point on each device. Now, the next tenet that I want to share with you is really the crux of our talk today. How can we exploit the system cost effectiveness over the lifespan of these devices with new intelligence? What we want to do is use paradigms such as model predictive control and model-based calibration in order to refine and redefine the way that these systems behave at the edge. And what we're going to find out later in this talk today is by using Amazon Web Services, we can do this iteratively and quickly between the cloud and the edge. The next tenet, which our customers have been doing for some time now, is having the ability to make better decisions through centralized dashboards and monitoring. Our customers today use AWS CloudWatch in order to centralize all of these log file informations and then present those into dashboards to make better decisions. Now, the next slide is related to the second slide that I showed you before, the second tenet, where we want to be able to derive value through these new capabilities quickly over time. We're going to redefine the way that these systems behave, but how we actually package that up and deliver it is going to be refined. Now, in the Xilinx case, when we're working with FPGAs, we repackage these capabilities through IP blocks. These IP blocks are applied onto the FPGA to give these capabilities at the edge. Now, what we want to be able to do is repackage those bit streams and deliver those to the edge quickly and simply. And using technologies such as connectors, we'll be able to do that. Now, what does that look like in a real case scenario? What you see here is a natural gas pipeline system. In the center is the main compressor unit. These main compressor units are huge and they're very much high-value assets. We want to be able to protect those assets. And throughout the pipeline, you'll have other components that we need to care for, such as cooling systems and backup generators. All these components need to communicate effectively together. Now, when we're talking about managing these particular components, we want to be able to narrow down what exactly we want to control. Many times in the past, these were all controlled using field bus protocols. And if you're doing command and control with these systems, in the future, most likely they will continue to be that way. But what we're seeing more and more often in mixed criticality systems is that we're placing not just a centralized system to control all these other entities throughout the ecosystem, but we're seeing compute being placed at these other components to actually communicate with the centralized system in non-critical ways. For example, just relaying telemetry for analytics purposes. So really, what we're really going to focus on later on throughout this talk is AWS IoT Greengrass, being able to do object classification at the edge and working hand in hand with Amazon FreeRTOS in these less compute-intensive areas. So let's go ahead and take a look at what that looks in the big case of the industrial IoT architecture. So let's take a look at the industrial IoT architecture. On the left-hand side, what you see are the physical components that we just talked about within the natural gas pipeline scenario. On the very left-hand side are devices that would be running Amazon FreeRTOS, those small microcontroller devices that are most times doing sensing, but can also do actuation. Those devices relay information to a gateway system, and in this case, it's running AWS IoT Greengrass. A Lambda function can be used to interact directly with the field bus protocol, maybe over, for example, an RS-485 line, a serial protocol. Now, what we want to be able to do is take that information that we're getting from the edge and bring that up into the cloud. What we'll be able to do here is, naturally, is AWS IoT Greengrass connects with AWS IoT Core. It connects to AWS IoT Core over a TLS 1.2 mutual authentication connection. Now, one of the patterns that we want to always put into place when we're taking in ingest from the edge up into the cloud is fan out data to a wide variety of systems. In this particular case, we're actually taking the data that we're getting from the edge and we're placing that into 3 different areas. Up at the top, what we're doing is that we're using Firehose to gain this information so we can ultimately put it into some other compute areas, and I'll get into that in a moment. What we can also do is curate that data directly into AWS IoT Analytics. Now, up on the top, if we go through this, what we can do is actually put this through some more analytics pipeline. Through this analytics pipeline, we can put it through compute in AWS Lambda to understand if we actually have an issue at the edge that the customer needs to go out and action. AWS Lambda can send a message to SNS and then alert a worker to go out and do some work out on the work site. Also, what we can do is we can do anomaly tracking. So we can fan that back out to Kinesis and then put that into an anomaly repository. And then after that point, we can curate that data and actually take a look at that data using Athena so we can ultimately view that within a dashboarding system. Now, what many times our customers are doing today is that we're putting that data directly into S3 in order to curate a data lake. We'll be getting into data lakes a lot in more detail later. But what you can see here is that our customers are actually building up this data over time and then having the ability to visualize that with the help of Amazon Aurora. Now, what our customers are also doing is using SageMaker to take those data from the data lakes, curating it, building machine learning models, placing that into an S3 bucket, and then delivering that back down to the edge using AWS IoT Greengrass machine learning. And then over time, through the life cycle of this device, our customers are using Glacier to place that data into long-term storage, possibly to bring it back out to do some analytics at a later time. So let's take a look at what that architecture looks like within the machine learning lifecycle. The lifecycle needs to be iterative, and data flows from one area to the next. Let's start off in the lower right-hand corner where we're talking about physical devices in the environment. These physical devices usually operate on-premise on hardware that you own and operate. Software that's provided to our customers that runs on this hardware that you own and operate includes AWS IoT Greengrass, Amazon FreeRTOS, and also a variety of device SDKs that we provide to have a simpler way to connect to AWS IoT Core. In the lower left-hand corner of the slide, what we see are a variety of ingest mechanisms, ways that we can provide data from the edge up into the cloud. Up in the upper right corner, what you see is a variety of storage mechanisms, ways that we can store data and also curate data for machine learning, which leads us into the upper right quadrant, which enables our customers to build machine learning models so we can be more effective at the edge. When we're talking specifically about the work that we've done with Xilinx, let's take a look at the lower right-hand corner. First, I'd like to talk about the UltraScale Plus processor, which is a mixed criticality processor, which enables you to have one part being normal compute, an ARM core, and the other part being the FPGA fabric. And they have the ability to work together. The other processor that we've been working with is a Zinc 7000 processor, which is actually a dual Cortex A9 processor. And again, it has FPGA fabric on it to be able to do some acceleration. In the upper right-hand corner, in order to build those models that run on those processors, we use the Xilinx DNNDK, which is the Deep Neural Network Development Kit. And that works hand in hand with Amazon SageMaker. So let's go a little bit deeper about feeding the data lake in order to ultimately enable building the machine learning models so we can do something more effective at the edge. And that is on the lower left-hand quadrant of the cycle that we just talked about. So in the beginning, our customers will not have any data up in the cloud specifically for the data lake. Well, you may have some data, but it's not really in a format as in a data lake. What we want to be able to do is take data that you're generating at the edge and be able to put that into a series of S3 buckets that enables you to build this data lake capability. So how do we get that data up into the cloud to build the data lake? Well, there's a few ingest points that we can talk about, and really they're specific on a use case basis. The first ingest point that I would like to talk about is just the normal sensor. The normal sensor is just a lightweight device, a lightweight microprocessor system that can connect directly to IoT Core over that TLS 1.2 connection. Now from that, what we want to be able to do, depending on the rate of course, the velocity of the data coming in, is relay that information into Firehose so we can batch process that into S3. That's one pattern. The next pattern that we see very often is video data. With video data, we have the ability to take data from cameras and put that into Kinesis video streams, which can then put that data directly into an S3 bucket as part of your data lake. Now, the next case is really a very interesting case where you can have offline data or super slow connectivity speeds. In that case, what we'll want to use is a snowball system. And from that snowball system, after you're landed in your airplane or in some other environment, then what you can do is ship that component directly back to AWS. AWS will put that data for you into S3. And the last case is another pattern that our customers use, which is a way to really proxy data through several systems to streamline operations, where we can ingest data, like the first case that we just talked about, ingest data into IoT Core, put that into DynamoDB, and then use DynamoDB streams to put that data into a data lake into S3. So let's talk about curating the data lake, because really just getting that data into S3 is the first stage. What we need to be able to do is take that data and refine it. So let's take a look at the upper left-hand part of the quadrant. These are some capabilities that we provide in order to curate that data. So you have a bucket full of objects that you want to use possibly to build machine learning models. Well, if you need to slice and dice that data, what many of our customers are using is EMR, Elastic MapReduce. It's on the upper side, and they can take that data, slice and dice it, and put it into another bucket. And you might ask, well, why can't I just put it into the same bucket? Well, what we want to do is keep the data in its original state, its original untainted state, just in case you want to go back and use that untainted data for another purpose. Another way that our customers manage that data is by using SageMaker. Some machine learning algorithms require specific formats of data. So you can actually use SageMaker Notebook to slice and dice that data, and then place that data into another S3 bucket. Now there's another capability that's called AWS IoT Analytics. And IoT Analytics has the ability to streamline or pipeline the modification of that data into data sets. That's just another capability that our customers can use to take that data. And that data can be ingested directly into AWS Analytics or actually proxied through the AWS IoT Core ingest point. But really, our customers are doing this in an iterative basis. And really what we're finding is that cleansing this data can sometimes be more art than science, because the way that you slice and dice data and feed that to machine learning algorithms can modify the way of those outcomes come into effect. So taking into account the data lake, the curated data into S3 or AWS IoT Analytics, and feeding that into a SageMaker notebook, the data scientist needs to take a look at that information and understand, is that really giving me the intended results that I want? And they'll look and do annotation and cleaning and maybe change the data types of the data that they're curating and go back and reprocess that data from the original data lake data and put that in and reformat that data and put it into another format to potentially improve the results. So that's what I mean. It's really more art than science. It's iterative, and there's a lot of inspection that needs to go on. So let's talk about the training and staging with doing the machine learning at the edge. That's in the upper right-hand quadrant. Now, we saw this slide last year at reInvent 2018, where we have the 3 stages. Down at the lower level, we have the compilers and the infrastructure. In the middle case, we have SageMaker, which is a set of components within the SageMaker service that enable you to quickly iterate on building machine learning models. And then we have many services up at the top layer there that enable you to quickly get started and in many straightforward cases, leverage these services to build your solutions. Now, when we're taking a look at what we're talking about today, really we're looking at the lower 2 levels. We're looking at the compiler, the model compiler level, and what compute that we're using in order to achieve those outcomes. And we're also looking at SageMaker to assist us in managing the computational algorithms and getting the models built and staged. The way that we do that from a SageMaker perspective is, first of all, you'll be using a development language such as MXNet or PyTorch. In the middle column, what we'll see is actually model compilers. You need to use these model compilers to take the inputs from the algorithms and output that into a physical binary or bit stream that needs to be deployed to the edge. And then what you can see down at the bottom is Xilinx DNN-DK is there, and there's a couple of ways that you can actually, on the left-hand side, use the DNN-DK that I talked about previously. One is by using TensorFlow, and the other is by using Caffe. So let's talk about feeding that data into some compute so we can perform those computational algorithms against that data. On the left-hand side, we have SageMaker. Actually, what we're doing is that we're putting in all of our instructions, how we want to evolve that data via an algorithm into a model in a SageMaker notebook, which is a Jupyter notebook. Those instructions are sent to an instance, an EC2 instance, which enables you to compute that at a higher rate. Many of our customers today are using P3 instances to do that work. Now, we need to take a lot of data into account in order to build those models effectively. You've probably heard that the more data that you have, the better that your model could be. Well, as long as your data is curated in the right way. So on the upper right-hand side, we need to feed in all that curated data into the P3 instance and use those curated data sets from AWS IoT Analytics as well. And with that, what we'll do is that we'll bring in the model compiler. It's really a container. It's a containerized function into the P3 instance to perform this compute altogether. And remember, SageMaker is really the item that orchestrates all this work through a SageMaker job. And eventually what happens, after this compute function is performed, a binary model is output. That binary output is put to an S3 bucket. So Really, what we're doing in this case is, again, taking the notebook on the left-hand side, applying the instruction to the P3, and then from that compute function, putting the model out into an S3 bucket. But really, just putting the model to an S3 bucket doesn't do us any good when we're working at the edge. Eventually, what we need to do is take that model that we've produced up in the cloud and propagate that to our edge endpoint so we can increase the value of those systems that we've already invested in. So let's talk about inferring at the edge and exactly what that means based on this model that we built up in the AWS cloud. So let's talk about the lower right-hand corner, about the actual physical compute instances and how we can get those models down to the edge. Well, let's go through this diagram step by step in order to understand how we're going to compute that. Actually, I'm just joking. What we're going to do is just talk about a couple of blocks in this diagram. The upper left-hand block is actually the compute portion, the ARM core portion, which runs embedded Linux, which AWS IoT Greengrass runs on top of. On the lower portion of this diagram, you actually see the FPGA fabric. Now, in the inference case, the lower part of this diagram is actually what's performing the object classification. So the model that we built in the previous section of the slides is going to be built into a bit stream, eventually propagated down to the edge, and then applied to this FPGA fabric, which is in the lower part of this diagram. Let's take a look at this mixed criticality system and see exactly what that means and where we're placing all the software. So if we look at it from a chip perspective, one side is called the PS side, or the programmable system side. This is where we're running Linux. And then once we have the Linux running on that system, then we can apply AWS IoT Greengrass to run these inferences at the edge. At the right-hand side is the programmable logic. The FPGA programmable logic is really a bunch of logic gates that you program on the fly. How does that really look from a pinup perspective, though? If you look on the other side of the processor, you'll see a bunch of pins. And somehow the software within that system needs to work against these peripherals. On the left-hand side, you'll see a bunch of pins that are aligned with the programmable system. And on the right-hand side, you see a bunch of pins that are wired up to the programmable logic. And what you may be able to infer from this then is the logic that you define for your FPGA is programmed directly against some arbitrary pins that you define and then ultimately make as part of your design. What you can also infer is that really, because Linux is not a deterministic system, is that you can actually build deterministic systems on the programmable logic side. That means that you could define the logic to be super fast, super reactive, which makes things better for working things like cameras. So you can define your programmable logic to work directly against the camera signals and then feed the data that's being acquired from the camera directly into the object classification code on the FPGA and then give the results to the programmable system side. So then what you can begin to glean from this is, all right, if I can combine AWS IoT Greengrass with the model build process that we just discussed in the last system, deploy that model to the edge, and then update the FPGA on the fly, that would make the system a lot more reactive. And you can evolve the object classification and the model system over time. So when I actually begin running the system, I will use a Lambda function to begin invoking the programmable logic from AWS IoT Greengrass. And remember that programmable logic is wired up to a camera, and then it'll begin inferring. Now, if the programmable logic is written in a way that it can do the object classification, which we would define with the DNN-DK that we discussed in the previous section, then what we can tell the programmable logic to do is to output the classified objects between the shared memory system, between the programmable system and the programmable logic. Now, once the programmable system side can acquire that data from the memory, then it can output that as a regular file to the file system. And you would have to clean that up over time. Now, you may think, well, you have to actually have Greengrass talk to the memory and all these peripherals in order to make it work. And that's right. And Greengrass has special constructs built in to limit the actual hardware peripheral footprint that the application has access to. So one Lambda function may have access to the I2C and UIO peripherals on the system, and other Lambda functions may have access to devmem in order to acquire those images. Now then you may think, well, I need to somehow take those results and bring them up to the edge. If you remember in the very beginning, the industrial architecture slide, what we want to have the ability to do is to take those changes out on the edge and bring them up into the cloud so I can actually perform some interesting work with them. Not only that, but if we can acquire those images on the edge and put those images up into the cloud, then I can further build up my data lake to improve my machine learning algorithm over time. But we need to have an effective way to transmit those images up into the cloud. It wouldn't be very effective to transfer those images through MQTT. So what AWS has put in place with Greengrass is the token exchange service. And the token exchange service enables you to communicate directly with virtually any service in the AWS cloud, including S3, based on the role that you apply to your Greengrass group. Now, if you're generating a ton of data, if you think back to the slide where we were talking about ingest capabilities, if it's really too much data, even to put directly into S3 over the network, maybe it's just very, very thick data, then you can always apply that to Snowball and then send the Snowball package up back to AWS, and AWS will put that data into the cloud for you. So to recap, this is just to talk through the life cycle once more. Remember, this is an iterative life cycle, and the information flows one to the next so we can generate data from the edge, ingest that into an ingest point according to your particular use case. That could be IoT Core, that could be Kinesis video streams, and that could even be a Snowball instance. Once you have that ingest point implemented, you can proxy that data into a variety of storage mechanisms. And you can use technologies such as Elastic MapReduce to take the data that you've put into an S3 bucket, slice and dice that data, and curate that data over time. Then what you want to do is improve that intelligence over time. The way that you can improve that intelligence over time at the edge is by rebuilding models, machine learning models, using the data that's been put up into the cloud. And you can use that by implementing SageMaker and building the models through Amazon SageMaker and placing those models back into S3 so they can be deployed. Once those models are deployed back into the edge, then you can use those models to actually action that improved intelligence. And thank you. My name is Richard Elberger. You can contact me on my contact information on this slide. I'm looking forward to speaking to people about building industrial applications at the edge.